Okay, hello everyone. So today we will proceed with track number 2, where we going to re-establish the alignment using GEDO NovaTrack, just a different approach using the direction analysis. And for that, for this track, I have selected a different group of measurements made with GEDO trolley system with GEDO horses. And as you already know, for the calculations for initial data we use GDT file format. So I select exported data from GEDO Office, and here we go with analysis method called REHAB. So first of all, I will just go give you a quick overlook as in the previous track. What we see here, what the basic information is, basically we see then the length, the total length of measurements, so the start end chainage, and the amount of points which were read from the file, and amount of points which are deleted due to the redundancy, overlaps, duplicates, and or maybe too high divergences from the main line. Also, we see how many points will be used in the calculation. So 3,429. Further on, we go to the configuration menu and give some preliminary numbers, preliminary constants for the calculation engine. So we get some first attempt with the numbers we expect. So first of all, I define the minimum straight line length of 50 meters. You can say 30, or it can be more, so that is more or less your expectations or maybe regulations. Then we set the maximum movement of the elements, so the calculation engine stops when the elements are not moving more than 5 centimeters. And here I give the radius for the radius which will tell the software how and when should be the transition curves added to the circular curves. So basically it means that 3,000 meters, all the radiuses below will contain the transition curves at start and end. We confirm by clicking OK, and then we go for the calculation, press OK, analyze. Yep. So we have in the top view, we see the calculated horizontal alignment. So each color represents the type of the element. If we zoom in with this zoom tool and then click on the edit and we scroll through the elements, you can see that the green is for the straight line, red is for the circular curve, straight, circular. So basically what we are missing here is a transition curves, which actually are the blue color. We can zoom out to the extent level, and yeah, the same is at the other end. So in between we have the long straight line. What is interesting here is that we should always take care about the vertical and the horizontal offsets, which actually tells us how close the calculated alignments, both horizontal and vertical, are diverting from the original track position. So the scale actually by default is for horizontal is -+20 centimeters, for vertical is from -10 to +30. To be more precise with adjusting elements on the further steps, I would highly recommend to go to the tools and adjust that vertical horizontal offset scale. So we go tools, options, and we select, for example, 5 centimeters for horizontal and 5 centimeters for vertical. I would say we can change the speed in the beginning leave it as it is. And then we say that I would expect minimum uplift of vertical alignment of 15 millimeters. For further usage, I would recommend to save these settings as user default, so you can reread them at the next projects. So by clicking save, it will save as a constant. And then when you start a new project, you just simply can recall them by clicking get user default values. Alright, then we click OK. Yeah, this says program that speed has been changed. Do we want to recalculate the speed and cant values? Yes, sure we want, and we click yes. And here we see that scale has been changed, and the offsets are more visible. So the black line represents existing track position, and the center line of the diagram is the design position of the track. The same for the vertical. Just it depends more on the scale. So if you be more correct with selecting the scale, you might get that a 0 value in the scale diagram, which would mean that this is a design position, and the black line is the position of existing points or existing track. So then we will move further on. As you see, we did not are fully satisfied with the solution, because first of all we are missing the transition curves, and we still would like to have them here. Second, we want to be more precise to defining the beginning and end of each element. So in order to be really close to existing track and to get a good solution, today we will practice with a analysis method called analysis using direction diagram. So we click on the analysis icon. We are moved automatically to the analysis window, and here first of all would like to mention that once we activate the analysis window, software automatically brings us to the curvature 7 diagram, which means all points are represented as a result of inverse curvature through 7 points, inverse radius of 7 points. So this method was overviewed in the first track. Now we go to the direction method. So please select direction method, and these are the same points, just shown in a different way. So diagram shows how the points are diverting on a direction, on a direction base. We also can see there are some points which are off the track completely, so it might be some measurement errors or really bad quality of the track. I would recommend to delete those points by pressing Shift key, keeping Shift key down, and just move mouse over the point and press delete. So the points are deleted. Of course they influence element position as well, so yeah. Okay, so we have the points. We a bit clean up the diagram from unnecessary points, and then we want to get the first calculation of diagram, get some preliminary data about how the alignment element should be displaced, located. So let's press Shift P letter, and here is a tool which allows us to give to calculate draft position of the alignment elements in horizontal using the change of radius. So the software will analyze the radius of the points, and upon changing the radius of a certain set number, it will create a split point and will create another radius. So I would say as a track is 3.5 kilometers and more length, we set 70 points to analyze, use 50 points to create to analyze direction at the beginning, analyze a radius at the beginning, middle and end, and if the radius is changing by 1% plus minus, it will create a new element. Click OK. So we have first calculation, and you see there are many split points, which means that element radius is changing and it's creating new and new split points. So this is definitely too much. We will not get into any good solution. I would recommend you to delete redundant split points, so each element has one at the beginning and one at the end. Speaking about this diagram, I can mention too that each color represents the meaning of the element. So the green is for the straight elements. We have the okay, let's first delete. So the blue color is for the transition curves. Yeah, we delete again. If you move mouse over the split point and press delete, it will be deleted. So we take away all unnecessary points. If we want to insert point, just press insert key and just confirm OK. Right. So the next step is that when I started to explain, each color represents the type of element, and the next thing we would like to do is to adjust the straight element directions. So if you go on the beginning of each element of straight element and select the move mouse over the split point, press A letter key, and the element will be automatically adjusted through all measured points. The same we do for the next straight element, and the same we do for the next. Okay, so we adjust the position of split points just sliding up and down. You can see that the auto snap is active, means that the split points are automatically locked to the measurement data. All right. If it suddenly changed the color, just press again A on the beginning of straight element, and it will be averaged to all the measured points. All right, so we have finished. It's important here that please take closer look that straight elements do not have any split points in the middle or anywhere along, because that might be run into the unsolvable solution. So inspect the elements. If everything is clear, then just right click and run calculate. So we calculate horizontal alignment, and the horizontal offset diagram is changed too. We can now minimize this window, or just press the horizontal view icon in the top toolbar, and here we are again back to the initial view. So the next step is to adjust each element. So we push offset down to the required level. We right click on the window anywhere and then select normal edit mode, and we just, you can see, we can scroll through the alignment. What we further do is you see there are some large offsets on the circular curves, meaning the wrong radius, the wrong length. Also, we will adjust the length of the clothoid, so they are influencing these offsets too. To push down these heights offset to the middle, first of all, I would recommend to you to start with the transition curves. So we double click on the element, you see it's highlighted, and we just changing the length. You see how the offset horizontal offset diagram is affected. So keep pushing down till you are more or less satisfied, and then you can go to the next transition curve and do the same. Yep, it's getting close. You can also type in the number, I mean the length, it's like 100 meters. Press calculate and it will be affected immediately. So can be a bit faster. Okay, so we're almost done with this curve. Then we move to the straight element. As you can see, all the straight element is drifted to one side. It meaning too many temping values will be just to one side, and to avoid this, we can lift or shift the complete design element to one or another direction. So there are 2 points, first entering points, first point and second point, meaning start and end of the straight element, and I just adjust the beginning, the end of this element. We can also do the same with the beginning, and then we go to the next curvature. And we can adjust the radius here. Okay. Let's try 15,000. Oh, we can even delete that element, put the clothoid. Alright, so we are almost done. If we are satisfied with the horizontal alignment solution, we just close this window. And then we move to the vertical offset, to the vertical alignment. So vertical alignment is activated with the next icon, which is vertical alignment icon. And here we see the bending points of the break points of the vertical alignment. So these are the parabola elements, and the center points indicated is with the radius and the change. So how we will proceed here, it's very similar way, just we don't use diagram here. Instead we use the insert angular point tool, and if we click anywhere on diagram, the software prompts to give us a radius for the new parabola element. So depending if it's we are below or above the measured points, we can give the positive or negative. In this case we are above, so we give the 5,000 radius, and the software automatically inserts element. The next thing you might want to do is still to continue adjusting. So if you double click on the element. You can adjust the Z value, which is actually the elevation, moving the element down or up. So important to know, if you set in the constant that you expect a minimum uplift of 15 millimeters, the software, when you insert a new element, the software tries to push the element to this desired level. So however, you can continue adjusting using the elevation or the chainage. So if you highlight the parabola, the STA, it's a chainage, so you can adjust the chainage either by clicking on these arrows or just typing in the value. Okay, so we now continue with the next elements. I will adjust a bit the elevation so we are on the right level. We can move a bit of a position of the curvature, and then we can move to the next points. We just adjust the position of vertical curvature and insert the new angular points. You see the software automatically adjusts elements to the required level plus 15 millimeters. And we add one more. And here we can zoom in and check what is status here, and we see the big bending, so we might insert again. And then if you select the middle point of the parabola and move with the mouse, it will be shifted to a new chainage, so it's a bit faster to get a desired result. Okay, so we put again one more point here, and we are almost done. So the same principle applies to all further editings, adding the breakpoints for vertical curve. Important here is that each insert angular point is a parabola point, so you can't have the breakpoints without parabola. It should be a parabola. Of course it can be very short length, like a few centimeters or so. When we finished with vertical alignment, the next step is to go to the CAN calculation. We select Tools, CAN Speed Calculation. We go to the Speed tab and click here to calculate. So the software automatically calculates the CAN values and on H1 and H2. And this is the speed, the recommended speed by default. To override these values, we can just give our own numbers, like start the cant for the transition 0 and cant, we can say 90. It continues with 90 through the radius, and then it approaches another radius. There are two radius interconnected, and then from 90 it goes again 90 and ends to the straight with 0. And then the same, we have another clothoid. So we have from 0 to 100. We can accept this, and then we continue with a constant radius and a constant current, and then we descend from 100 to 0 as that it is a clothoid. We can scroll down to the next elements. If there are no in the list, we are finished. So to fix these changes, it's important to remember that we need to activate the cells or the records which has been changed. So we just click activate. It means that we overwrite the initial proposed values with our own values. Okay, so this is done, this is finished, and then we press OK. You see the speed diagram has been adjusted, and the next, it just basically tells that it highlights as it has been overridden by the user. So I overwrite the values because I activate this command. And the next step is store all those calculations as the project. So we just press save, and we get the extension SPV. So basically SPV is a default format for the project, whereas if we want to use this data for the in GEDO office and then move it into the field applications, we have a direct saving to the GEDO office files. When we select the name, for example, we go to the folder where we store the data and we give a name. Test track 4. It will automatically add the GEDO office alignment extensions TDT, HDT, and UDT. So you don't need to add any additional extension. Just put the name and press save, and the data is exported automatically into 3 different file formats. Yeah. So we are finished with this lesson, and thank you very much for your attention.